Good day, everyone, and welcome to yet another episode of Anim Chemist. In this video, we'll cover one of the most outrageous and scary ways to die. Firstly, what exactly can be outrageous scientific deaths? A mishap in the lab? A mass breakout of nanobots? No, today we're talking about nuclear chemistry. We talked about isotopes before. Those have different numbers of protons and neutrons. However, not all isotopes are stable. Unstable isotopes emit or change protons and neutrons to be stable. Those particles can be unusual or harmful. We'll talk about them later. There are 3 ways that unstable isotopes can use to decay into stable isotopes. The first way is called alpha decay, and it is ejection of a helium nucleus. Yes, it is that simple. 238 you can decay into 234 thorium through alpha decay. Ejection of 2 protons and 2 neutrons. Even though the new thorium nucleus can still decay, it no longer emits alpha particles. Beta decay is harder to visualize. There are 2 types of beta decay, beta minus and beta plus. Beta minus decay is a process which emits an antineutrino and an electron. The sign behind the beta symbol will correspond with the charge of the ejected particle, e.g., beta minus ejects a negatively charged electron. The opposite happens inside the nucleus. During beta plus decay, a proton converts into a neutron. The overall charge in the system always stays the same. For example, 90 strontium decays twice using beta minus decay. This results in zirconium-90, which is stable. Strontium-19 changes 2 neutrons into protons and ejects 2 electrons in the process. There's also a type of decay called gamma decay. Some nuclei are unstable simply because it has too much energy. This excess is released as extremely high-frequency light. This frequency is called gamma rays. I know, very surprising. Those ways of decay are relatively less destructive towards the original nucleus. Sometimes we fire neutrons at radioactive atoms and they split down the middle. It's true. When a nucleus splits, it gives off a bit of energy and sometimes more neutrons. Those extra neutrons can fire out and split more nuclei, which fire more neutrons, which split more nuclei. This is a chain reaction that happens in nuclear power plants. A common nucleus to split is uranium-235. This splitting process is called nuclear fission. Beware of those reactions though. Gamma rays are highly dangerous. They can kill living cells or even cause permanent damage to your DNA. Thankfully, neutrinos and antineutrinos don't interact with matter much, so they won't be dangerous unless you stand inside a supernova. Most isotopes that undergo fission and decay are radioactive. Please do not go near radioactive elements without protective gear. Radioactive elements are known for causing permanent cell damage. There's also a way to produce lots of energy in a single burst: fusion. Nuclear fusion is the opposite of fission. It is the process of smashing nuclei together at high speeds so that the nuclei combine or fuse together. An example of nuclear fusion is deuterium, 2 hydrogen, fusing with tritium, hydrogen 3, to produce a helium nucleus and a neutron. This fusion process actually happens inside star cores and gives them the energy to shine. Now that we've introduced you to most types of radioactive decay in combination, it's time to see if you remember them well. Imagine that carbon-10 undergoes beta plus decay. What does this produce? Well, the daughter nucleus, I don't know why it's daughter and not child or son, would have 1 extra neutron and 1 less proton. This points to boron-10, which incidentally is a stable isotope and does not decay further. The released particles would be then a plus charged electron and a plus neutrino, or 1 positron and 1 neutrino. Conversely, if carbon-10 underwent beta minus decay, the daughter nucleus would be nitrogen-10. Sadly, this is a short-lived radioactive isotope which can only be produced artificially, and it has, as of now, no purpose whatsoever. Also think what would happen if you shot neutrons in plutonium-239. The reaction breaks the plutonium atom and results in xenon-134, zirconium-103, and 3 more neutrons. Those neutrons split more plutonium-239, which released 9 neutrons, which split plutonium-239, which released neutrons. This chain fission reaction is just like the uranium-235 reaction in power plants. Well, that is the range of nuclear modifications. I hope that you managed to learn how to know the parent and daughter nuclei and what a specific decay mode releases. Oh, one last thing. Don't go near radioactive stuff.